So shall we start now or want to wait for a couple of minutes?
Yes, we can start.
Yeah,
Okay.
let's start now.
Yeah. Good morning,
Yeah.
everybody. Welcome to day 2 of the Spark workshop. Our first speaker is Vishal Benjamin from IUCA, and he'll be speaking on accelerating space weather forecasts with deep learning and interpretable AI. Vishal, you can take over from here.
Thank you, Yoshita, and hello, everybody. Hope you're having a great time in this workshop and learning a lot of new things. And extremely sorry for this internet issue. This is not, certainly not in my hands. I could have gone to the institute, and maybe the net was better there. But the hotel internet seems a bit weird. So much for a space for the workshop and a machine learning talk that we can't get the internet working well. But anyway, so I'll be talking to you today about a bunch of techniques through which you can accelerate space weather forecast. So by accelerate, I mean you can accelerate algorithms in terms of speed, and you can also learn new stuff from these algorithms and see how they can be useful to do science. So I'll be giving you two examples of my work. So let's see what how we do this. Okay, so next please. Yeah, so this is a typical a PR image I get from the NASA website on the various missions in heliophysics, and you can see that the whole of space is almost littered with instruments for studying the sun, the interaction of sun and Earth, for the interaction of sun and other planets, and even the interaction of sun and the interstellar medium. So there is a lot of data that is being collected all across the heliosphere. And there is also a lot of science being done because you keep getting new data and it keeps challenging our theories all the time. And so this presents us, especially heliophysics. Astrophysics itself is a very data-driven field, but heliophysics in particular, because of the large amount of data that it possesses, it provides an opportunity for using data-driven algorithms like deep learning to accelerate whatever things we can do. So these are algorithms that you have seen, they thrive on a lot of data, and given this amount of data that comes in, so and you have new missions coming up. For example, Muse is coming up really fast, and Aditya L1 that you must all be knowing about. It's going to be at L1, and it's going to get new data. So you keep getting new missions, and it's everywhere. So because of this large amount of data, you sometimes want to use ML if you have defined your problems correctly. So next, please. Yeah, so I'll give you two examples of deep learning. So yeah, so the domain knowledge first. So before we jump into using any algorithm, we need to have some domain knowledge. And I mean, you should actually have a lot of domain knowledge because deep learning algorithms are like this. You throw in garbage, you get out garbage. So you don't want that. You want to be very precise in the way you define your problems. So you need to know what is going on where. So this image that I show on the right side, that is the solar surface or the photosphere of the sun. And next, please. This is at around 5,500 degree Kelvin. But then if you go to the solar corona, which is next, please. So if you go to the solar corona, you see that you see these various loop-like structures in the very bright regions. So in the photosphere, you had these dark spots called sunspots, and corresponding to them, you get these bright regions called active regions in many places. And these are, so you can see that there is this dichotomy in emission, if you want to think about, when you go from the surface to the corona. And if you look at the coronal temperature, next please. Yeah, it's around, it's more than 10 to the 6 Kelvin. So this temperature increases from the photosphere to the corona. So as you keep going up in the heights, the corona rises above the photosphere, right? As you keep going up in the height, the temperature of the solar atmosphere increases. And what this gives rise to is the, next slide. Yeah, next. There's a GIF that should play. So what this gives rise to is the solar wind. The solar wind is basically a stream of particles that starts from the sun and it buffets around in the interplanetary medium. And interaction of solar wind with various planets causes to various space to the effects. So the solar wind is basically just a bunch of particles that are sweeping through, and you can see that the corona is more bound to the sun, whereas the solar wind is more free streaming from the sun. So this is the kind of system. So this is like the defining the system that we are working in. We have basically very high temperature plasma trapped in the a very in a gravitating medium, and then this high temperature plasma is sort of expanding outwards, and it becomes free streaming. And then next slide, please. Yeah, and then as it comes to Earth, what we do is we measure the properties of the solar wind in situ. So these are just particle measurements, and if you next please, if you perform a measurement of the solar wind speed, for example, you see that it comes in two modalities actually. You have the fast wind, which is, as the name suggests, it's very fast. It's more than 500 kilometers per second, and you have this slow wind. So next please, you can see the slow wind there. The slow wind, as the name suggests, is very slow. It's like 350 kilometers per second. But the speed is not the only thing that's different. The composition of these two wind modalities is also quite different. So this tells us that since the composition is different, possibly the regions from where the solar wind emerges is also different. So you have a feed. So whatever wind you get, whatever free stream wind you get, that depends on the properties of this hot corona that exists in the sun. And next slide, please. Yeah, so if you look at the typical picture of solar corona, we have, so this is from the AIA 193 data, and you can see that the magnetic field lines are traced on top of this image. And if you look at this typical morphological structure, the structures present in the corona, you can find that there are these bright regions, there are these dark regions, and possibly a background over which these two regions exist. So next, please. So that dark region there, and it's not just there, on the other dark region near the bottom, these are called Cornell holes. So these Cornell holes are regions where the magnetic field is going radially outwards, and they have reduced emission because the plasma is not staying there. The plasma is being taken off into the solar wind, and it just doesn't stay there. So since there's no plasma there, there's no emission there, or apparently no emission there. And then you have the active regions. Next, please. So you have the bright active regions, which is in which the plasma is confined. So since the plasma is confined, it keeps you see a lot of emission there, and these are very complex regions. And then you have these bright regions and the dark regions. So the background that we again see is what is called the quiet sun. So next, please. So that's the background quiet sun. So it is an interesting thing. So all of these three regions, regardless of how they look, all of them are at more than 1,000,000 Kelvin. It's just the average temperature in these three regions that is sort of different. So when people who study the coronal heating problem, that is, why is this corona so hot? And as you go from the photosphere to the corona, why is the temperature even rising in the first place? So people generally would also want to study this background and figure out why this background is hot in the first place. So if you can figure that out, you can figure out why the other regions are also hot. I mean, that's the general idea. But then more to the theme of the talk, it is interesting to note that these regions are also sources of the solar wind. So next, please. Yeah. So the solar wind is basically known to come mainly from these dark regions called Cornell holes. So these it looks pretty obvious in hindsight now, right? Because you have these open magnetic field lines, and you see that the plasma is not trapped there, which means the plasma must be going somewhere. And one obvious sink for this whole plasma is the solar wind, and as it's just emitting outwards from the sun. So the interesting thing is, both of these modalities of the solar wind, right, the slow wind and the fast wind, both of them are in some sense correlated with the properties of the Cornell holes. The fast wind is very well associated with the Cornell holes. That is like it's a very well-known result. So remember this. So even if you don't take away anything from this talk, one thing to take away is the fast wind comes from Cornell holes. And the slow wind is a much more interesting character because some people have found its association with the Cornell holes. And if you go next, you will see that it is also, yeah, next please. Yeah, the slow wind may also come from the active regions. So it's more of the active region boundaries. So as these closed loops in the active regions interact with some existing open flux nearby, that may also release some of the plasma trapped in the active region into the solar wind. So this is another mechanism which people have been looking at, and people have found some form of a correlation, some association rather, not a correlation, some association between the slow wind and the boundaries of the active regions. So the slow wind association is a bit more difficult to understand. It's a bit more dicey, whereas the fast wind relation is kind of a much well known result for almost around 20 years now, I think. So this is the domain knowledge that you really need for understanding the solar wind properties and stuff like that. So you need to know where it comes from. So you need to know the properties of the regions where it comes from. So that's one of the most basic underlying things. So you go next. Next, please. So this solar wind, once it comes near Earth, it interacts with the Earth's magnetic field. So this interaction and whatever is happening because of this interaction is what is called the space weather that is near the Earth. So you must have also seen a lot about the space weather, and beautiful phenomena like aurora happen when you have this interaction of solar wind with Earth's magnetic field. But that's the more benign aspect of the space weather. It's like aurora hunters can go and look at aurora for all we know, but then it also causes a lot of problems, like you have increased satellite drag, so your satellites should just fall away into the ocean, or you can have electric grids which are just getting burnt up because you are having currents induced in the electric grids and stuff like that. So these are much more devastating aspects of space weather, which I do occur occasionally. I'm not saying they occur all the time, but then it has a dichotomy again of being kind of benign or in being kind of very devastating. So it becomes important to also study and even forecast, for example, what happens to the magnetic field or what happens to the conditions on Earth given changing conditions in the solar wind or in the sun. So next, please. So what do the current state of the practice models tell us? So I wouldn't say these are state of the art models, because then that would mean that I have compared all of them, in a very detailed manner and presented my results. The state of the practice models are those models which are generally being used by various people, and I'm being very loose with the definitions here. So this these are models which I see people have been using, but some of these models I don't have much of an evaluation. I just know that people use them. So if you go next please, we'll see one plot. So this is an image that I took from a paper where they compare various data inputs with various models for forecasting the solar wind properties. So there are two aspects to this whole system. If you want to think about, there are multiple aspects to this whole system. But one aspect to this, the heliosphere itself, is that you have some plasma starting from the sun, and it reaches Earth in whatever ways it wants to. It undergoes a lot of transformation while it comes to Earth, and as it there are multiple ways in which you can evolve the initial conditions on the sun and propagate them towards Earth, and that is basically the bunch of models that have been listed there. So what this paper did was they evaluated all of these models on a single data set, meaning that you have a reference data set and you want to understand how good or bad these models are. And next, please. Yeah, so if you look at, so what people have generally, or what these authors have generally done, is they have taken this data or multiple Carrington rotations and looked at the correlation between the parameters that these models predict and the measurements of these solar wind parameters by the satellites like ACE and WIND, yeah, that's orbiting the Earth. So this correlation is generally used as a very good metric for any of these forecasting models. And what they find is that by and large the correlation is around zero 0.6. If you consider even if you consider a very complicated Mhd code, or if you consider a very empirical measure based on what is called the area of the Cornell hole, for example. So even if you, regardless of what kind of measures you do, the performance gain, or rather the improvement in the metric for these algorithms is not great. So then the people started asking questions. Maybe it's not to do with the algorithm itself. Maybe there's something to do with the data, or maybe some approximations. Maybe we are approximating some things too much in some places, or maybe the way these codes generally work is that they sample the central near the central meridian of the sun for around one full solar rotation, and then they stitch them together and make up a full map. So possibly that is smoothing out some dynamics of the solar wind itself, and that's what is giving rise to these results. So it's a bit more, it's a very speculative kind of statement that we know that these things are not, these are great models by the way, but we want them to be better. And so what is it that we can do to make them better? So that's the question they ask. Now, more on the geophysics side. So once the solar wind comes to, let's say the solar wind has come to Earth, and it's sort of interacting with the Earth's magnetosphere, and you have all sorts of processes going on. So next, please. So there are, what people do is, a lot of people have written MHD code. So when Sissy has a very nice MHD code for simulating what is the response for the Earth's magnetosphere on of due to the solar wind forcing. So these are very nice models, but then also that there's also the fact that they are pretty slow. So let us say that tomorrow you know that there is something happening in the solar wind, and I want to know by how long in time these effects are going to come down to Earth. They're going to cause problems and stuff like that. The MHD code will take some time. So I think it would take so some of these codes do take a couple of months to evaluate. So by the time the storm has gone by and possibly your electric grid is all broken down. So there is a lot of work being done on that end, in optimizing these codes and stuff like
So
that.
just to
But
Vishal,
yeah,
to
yeah,
clarify, this is Divyendu.
yeah, yeah.
If you put in in situ data into the MHD models, if you wait
I
for the
see.
in situ data at L1
Mm-hmm,
and run the models, it's basically
mm-hmm.
impossible to get a prediction in time.
Oh wow. Okay. Okay. Thank you, because that then reinforces a lot of the work that's going to come up later on. So,
No,
so
you are
yes.
being a little defensive, but that is the truth. So I mean, you
Okay, I
really
see.
have to first forecast the wind and then put it into the model. If you wait for the in situ measurements, you have a
Mm-hmm.
lead time of half an hour, and then you can't really run your models. It doesn't make sense, basically,
Yes,
to have
I
a,
see.
I mean, you don't really have any window whatsoever for a
I
forecast.
see. I see. Okay. Thanks, Dipendra. So yeah, so that's so you heard from the expert on the MHD codes. But we also have what are called the empirical models. So next, please. Yeah, so these empirical codes, so what they do is they don't perform any forecast. Rather, they fit the perturbation measurements. So I'll come to what these measurements are later on. So what these codes do is they fit the perturbation measurements measured at various ground stations to some changing conditions of the solar wind. So it's more like an empirical model, and this fitting is very fast because you can do a SciPy LM or something. It's pretty fast. But then this is not forecasting; it is fitting, and these fits are not great if the changes are happening very rapidly. So rapid changes are not taken into account for these empirical models. And next, please. Yeah. So what happens is, even in these empirical models, what I'm presenting to you on the slide here on the right side is what is called a global model. So you want to know what the geomagnetic field is like all across the globe. That is one that's obviously what we always want to know. But then for some people, they start off with a particular station. So these stations are based on very real locations on Earth, right? So you can look at one particular station and see what is happening for the measurements of that station and perform empirical modeling on that. And those models are pretty fast because you can get results in under a couple of seconds. And you may even have some lead time for your forecast. It would typically be a forecast a couple of minutes into the future. So it is possible for very localized models, very local models, but global models are still not there yet. So we have at our hands, or at least I'm presenting there, we have multiple problems. I'm just presenting to you two problems. So the first problem is that we need if you have a good forecasting, solar wind forecasting code, that would be great. And second, more specific problem is that we don't have high time cadence global models of how these perturbations evolve over time. So we need a model for the Earth side also. So next, please. So the question we ask is, because physics has so much data, I mean, we are just drowning in data right now, can we apply a data-driven algorithm or some data-driven model to improve upon what all work has been done already and see if we could get something out of it? So that's the question we ask. So next, please. So what have we attempted to do? So that is so putting it up in a very simple manner. So when I say we, it's not just me who has been doing this. There have been a lot of groups working on this, but I'm showcasing my results, which I worked as a part of various teams. So first, we go next. This is a very nice cartoon, I think. Yeah, go next. So that's the sun there, and go next. That's a solar wind that's coming out from the sun, and then go next, and that's the Earth there. So that's basically the system that's present. That is a system in the consideration here. And if you go next, yeah. So the task number one for us would be to forecast the solar wind speed given changing conditions on the sun, and we want to do it in the purely data-driven manner and see if we can get something, some better estimate for the forecast when compared to these other models. And next, please. And we also saw that the solar wind interacts with the Earth's magnetosphere. So that's supposed to be the magnetic field of the Earth. And go next. So if you know the conditions of the solar wind itself, can we forecast the geomagnetic perturbations? Ideally, we want a near real-time forecast of geomagnetic perturbations. But can we forecast it into the future and also have it have a very quick set of forecasts possible or not? So that's the kind of thing we will be. These are the two problems that we'll be looking at over the course of this talk. So next, please. Yeah. So that's the task number one. So the task number one, for those of you who do machine learning, can be very simply stated in this form. We have a bunch of images of the sun, and we have a bunch of measurements of the solar wind. So we want to translate from one sequence to the other sequence, as simple as that. Of course, we are not doing a sequence to sequence kind of learning here. That's not what is being done. But then you can always do such stuff in the future. But this is basically the problem. And we are not putting in any approximations that are, or any of the physical constraints. So approximations is not the correct word, I think. It's more of the physical constraints that go into the system. You're not putting any major physical constraints on the way solar wind propagates and stuff like that. So what we do is we just take a bunch of images, we focus solar wind speed, and then we just don't want to leave it at that because we don't trust the machine learning as a black box. We would then want to dissect this forecast model to understand the predictions. So next, please. Yeah, next. Yeah, so that's the bunch of images that we have. So next, so this is like an animation that keeps going on. So next, so that's photometric image data. So what we have is the image data from AIA. That's like so these are the Cornell images of the solar atmosphere. What we do is we take up each of these images, feed it to what is called a pre-trained feature extractor. So in this case, we use a Google Net. So the AI images are like what 256 cross 256 in this work. They are 4K cross 4K in the full resolution, but no, your computers will die if you give that. So 256 cross 256 is also a very difficult thing to work on. So what we do is we encode this image into a vector, into a reasonable size vector. I think it's 700 or something in this work. So we encode each image as a vector using the pre-trained extractor. And next. Yeah, and then what we do is we have a time series now of these vectors. So initially we had time series of these images on the left side, but now we have time series of vectors. And these time series of vectors is what we then use to train this LSTM. LSTM is short for long short-term memory cells. So these are basically specific kinds of neural network which have some associated memory, and they can summarize over multiple time steps and generate a hidden state, which you can then consider to be the summary of all the inputs that's given to the model. So we take this bunch of vectors over time, feed it to the LSTM, and next, please. Yeah, and then we map it to the solar wind speed. So you can keep going next a couple of times, I think. Yeah, so you have around 8 years of data, and we have one forecast per day. Yeah, yeah, just go back. Yeah, just go back. Yeah, let's spend here a couple of minutes here. So this whole algorithm of the pre-trained feature extractor to the LSTM is what is we call the WinNet. So it's a very unimaginative naming scheme, but this WinNet code is all available on GitHub, so anybody can actually download and use it. But then the interesting thing is that we have around 8 years of data, and we have one forecast per day. So we have a lot of data, and we can use this data to train this model. Now, this feature extractor is not trained. So this is a pre-trained feature extractor. We don't we use only the first couple of layers to encode the images, but then the training is done only on the LSTM. So that's something that's important to know. So if you perform the training on the training set and evaluate on some testing set, what do we get? So next, please. Yeah, so this is a typical representative plot, wherein the blue color corresponds to the observations with the error bars, and the orange color corresponds to the predictions. And those vertical bars that you see are what are called the high-speed enhancements. So a good solar wind forecasting algorithm should be able to capture these high-speed enhancements well. So for this particular forecast, it's the Pearson correlation is around 0.61, and you have the other metrics there put up there. So you can see that the correlation is still 0.6. It's not like it's increased a lot. But then we didn't really solve any equations here, and this code takes like I don't even know if it takes a couple of seconds or not. It takes less than a second to actually generate the forecast. And since it's all vectorized operation, you can just give it a whole bunch of images, and it will generate a whole bunch of forecast values for you. And go next.
Vishal, if I may
Yeah,
interrupt, yeah,
sure.
there are two questions.
Yeah.
One by Devesh Bhattacharjee. He's asking, do you also predict solar wind magnetic field strength and direction using ML? Because magnetic field is also important for the geomagnetic perturbation at the Earth.
Yes, good question. In this model, no, but that is something I want to expand on. So, I mean, this is like more like a. So that was the first paper that came out from me, and adding the other parameters is more like a hobby now. So whenever I get time, I'll sort of sit and work on this thing, I guess. But if somebody wants to work on this and use this model, just feel free to send me an email or something, and we can sit together and work on it. But to answer your question, no, I don't do the I don't forecast any of the other parameters except the solar wind speed. This was just to a proof of concept to show that ML works for the solar wind stuff. Yeah.
Right. So there's another question from Prince Prasad is asking fast wind and solar wind, fast wind and slow wind are there. Are we talking about the average speed?
Yes. So the average speed of the fast wind is more than
Okay.
500 kilometers per second. Yeah. So and the slow wind is slower. Yeah. So that I hope that clarifies a lot of things because and it's a good thing you asked about the fast and slow wind because that's exactly what we are going to do now. So what we then look at is that we have this nice model which has been doing some forecast, and now we want to dissect what's happening in this model and see what kind of regions or what regions of the sun does the model deem important for generating a forecast. So the set of sequence of images that you see on the top are the input image sequences for 4 days, and then the forecast is on the 5th of June. That's given on the top there. So go next. Yeah, so if you look at the corresponding importance map, so GradCam is a method that is used to, I mean, there are multiple ways of probing these neural networks. So GradCam is one method, and GradCam basically is giving you a bunch of regions in the input side which are important or which the model deems important for a particular output. And for this particular output, which was a fast wind prediction, the model told us that 4 days before prediction, the Cornell holes are deemed important. So it just knows some dark regions are important, right? So it just shades every black pixel as large or whatever. So you can see that all of these Cornell holes in the third image, they are deemed very important. this importance reduces as you go back in time, and then you also see that some active regions are important, but they're not the coronal holes are sort of standing out in their importance. And this is 4 days before prediction. And if you go next, you will know that. Go next. Keep going next. There are like 3 points, I think. Yeah. So the first is the coronal holes are important, and the importance is highest for 4 days before prediction. And we know through correlation analysis and a lot of physical modeling that the fast wind typically takes around 3 to 5 days to come to Earth. So a coincidence in space and a coincidence in time can't really be a coincidence, right? It feels like, it seems like the model is actually learning something about how the solar wind is coming out. So go next. Yeah, I can go 2 more steps next, I guess. So here, what we show is the same GradCam result, but for the slow wind forecast. So this was again, I mean, you can see that's like 350 kilometers per second. And interestingly, the model says the active regions are now more important for the slow wind forecast. But it also says that, the coronal holes are also slightly important, somewhere closer to the prediction. So this got us all riled up because this is very interesting result, and you can go 3 points next, I guess. Yeah, yeah, a couple more. You get all the results there. So it is very interesting because the slow wind takes around 5 to 7 days to reach Earth from the sun. And typically it's telling us that, 5 days or 6 days before the solar wind is coming to us, look at the active regions of the sun, or that's what the model is telling us. And this was very, very interesting for us that if you go next. Yeah, so we didn't give it any equations for propagation of the solar wind from sun to Earth. And we didn't hard code any physical constraints in the model also, but then yet the model has seemed to have learned some mapping between the source regions of the sun and the measurements on the Earth. But then these are just like individual examples I'm presenting to you, right? So what if we do this, sort of statistically? So go next. So can we quantify GradCam activation?
Vishal, I have a
Essentially,
question before you get there. So when
yeah.
you say the correlation is maximized 7 days prior to the measurement of the wind at 1 AU,
Yeah.
what do you really mean by correlations? Are you inferring some statistical correlations between the images and the in situ wind, or is this when is the skill score for the prediction the highest?
No, so you can go back.
What parameter are you maximizing here?
Right, right. So you can go back to the previous slide. I can show it there, I guess. So what I'm talking about right now is just based on the inference from these images. So the parameter that's being presented in the bottom is what is called the activation. So it's basically, if it's large, it means that those pixels are more important for whatever prediction you're making. So for typical slow wind forecasts, active regions were deemed more important because they're redder, and that's very qualitative right now. So this is for a couple of images, we found this to be like really clear signal. But then we go ahead and quantify what is the activation per unit area, and we'll see the results now. So just in a couple of slides.
Dhruva has a question. Maybe somebody can unmute him.
Hi, Vishal, this is
Hi,
Dhruv.
Durga.
I
Yeah.
just wanted to ask you, when you say important, how important? I mean,
All right.
this is kind of, you are trying to attribute something to a set of parameters, right? And then how important they are, they should appear in some kind of scores.
Well,
Clear?
that is, I mean, GradCam is, I wouldn't say it's an extremely quantitative way of attributing importance of certain pixels to what forecast you're making, but it's not also a very qualitative way of doing it. It's somewhere in between. So when we did this work, a very large, the whatever activation value you get from GradCam, if it is very large, it would mean that those pixels are very important. Or so, because it was shown, I mean, it was shown in the original paper that you can have all sorts of biases creeping in your data, and they wanted to address these biases. So the skill scores, well, we don't really have a benchmark for saying that these particular regions on the solar on the images are most important for a given forecast. So since we lack this benchmark in the first place, we really can't attribute a skill score or something to the
Thank you. Sorry for the interruption. Maybe we should have a longer discussion later.
Oh, sure, absolutely, yeah, sure.
Uh,
So maybe I can just
Vishal,
quickly run over all the slides because we are, yeah.
Vishal, you have another 5 minutes.
Yeah, so I need to wrap up the other thing also. So let's go to the next couple of slides. Yeah, keep going next. Yeah. So just go like 3-4 steps next. Yeah. So what we want to essentially do,
Sorry, I
go
think
back.
there is another question from Ankush Bhaskar.
So maybe Ankush, you can wait till the end of the presentation and then I can take a question because I need to showcase the other result also.
Yeah, I think that's probably a better idea because
Yes.
we're running short of time. And I think Vishal can be
Exactly.
given 5 minutes additional because we asked a lot of questions in between and also we started a little late.
Thank you. Yeah, so what we basically want to do is this activation is just going to give you some numbers which are large for if the region is important, and they are small if the regions are not important for a given forecast. So what we do is we just segment out the active regions and the Cornell holes, and we look at what the average activation per unit area is like, and we just got a time series of it as a function of lag. So I use different methods here. Let's not go into the details here. So let's go to the next slide. If you look at the yeah, please go to the next slide. Yeah, I can go 2 steps. Yes. So what we have here on in the figure on the top left is that this activation value, average activation per unit area for Cornell holes in diamonds for active regions in filled circles, because Cornell holes are open, so it's open diamonds. And for the two passbands 193 and 211, so we just plot them as a function of how many when is the average activation peak prior to the prediction. And we see that the Cornell hole activation is peaking 4 days before prediction for 193 passband, whereas you see also some peaks for the active region activation some 5 days before prediction. And for the fast wind, we can statistically see that the model has deemed the Cornell holes to be important for fast wind prediction. But then the 211 image doesn't show this at all. I mean, there is we don't even understand what is happening in the average activation for 211 because it's going just increasing ever slightly, but then within the error bars it seems very consistent. And for the slow wind, it's very interesting that the both the passbands are deeming the active regions important, but then the time is missed. The time is 3 days before prediction. So just comparing this to what we know from physics, we see that some of the physics seems to be captured by these models themselves, but then a lot of it is also missed, and that's possibly because the model needs to be trained better, and we need to investigate more. But the bottom line is this: if we go to the next step, yeah, so some physics is indeed being captured by these machine learning algorithms if you are training them. And this was, I think, a very interesting result for us, that potentially you can evaluate these machine learning models by performing such activation analysis and stuff like that to understand why is the model thinking the way it is thinking something, if you assume the model is thinking at all in the first place. So that sort of was what. So that this sort of leads us to a bunch of different projects that we are working on source regions of the solar wind and stuff like that. So this is one way where you can accelerate your understanding of these machine learning algorithms for space weather forecast. So next, please. So yeah, so this second one, I'll keep it quite short because Lika ma'am is here. And this was something we did as a part of what is called the Frontier Development Labs. And so the geomagnetic perturbation forecasting that I talked about as the solar wind interacts with the Earth is the work that we did there. So you go next, please. Yeah, so what are these perturbations? Basically, you have some changing conditions in solar wind, and you can think of these perturbations as wiggles in the magnetic field of the Earth. And then these perturbations are measured all over the ground as a bunch of magnetometer stations. And go next. Yeah, next. So the basic idea is this. So we have a bunch of various measurements of the solar wind into the measurements of the solar wind. And if you go next, yeah, and you have the measurement of the perturbations on the ground, and those little white dots that you see on the globe on the ground, that's all this the location of stations where you have these perturbation measurements done. And what we want to do is, if you go next, we want to translate from the set of time series of measurements to a static global map of perturbations. So this map keeps evolving over time. That's basically what we want to do. So go next. Yeah, can keep going next, I think. So what we basically have is, again, we use so since it's a time series, we need to have some time series summarizer. So we have solar wind encoded in the form of a groove cell. We take the hidden state of this groove cell and go next. And so what this groove cell, the hidden state, contains is it contains a summary of all the changes that's happening in the solar wind. Not all the changes, but by and large, the most important changes that's happening in the solar wind. So we take that hidden state and we fold it through some fully connected layers, some appropriate layers. And then what we do is we take a basis contraction, the spherical harmonic basis. So all of these measurements are on a spherically symmetric manifold. So what we do is we just, what we are basically doing is we are just expanding out these perturbation measurements as a bunch of spherical harmonic coefficients. So we are enforcing the output of the neural network to be the coefficient of the spherical harmonic basis. So in this way, we can enforce a global, we can get a global map of the perturbation measurements themselves for given changing conditions in the solar wind. So does it work? That's a bigger question. So go next. So yeah, we call this model dagger. Yeah, go next. So this is storm time performance. So in the geophysics community, we have a couple of benchmark storms that are generally used for evaluating the models. So we go next. Yeah, so this is a typical storm time performance of dagger with the measurements at different stations. And the blue colored thing that you see is the dagger forecast. And by and large, the forecasts seem very nice. You are able to capture these variations in the geomagnetic perturbations at different locations. And if you go next, so those are the first column is for all those stations where the error was low, and the right column is for all the stations where the error was very large. And you can see that the dagger seems to have failed, in generating these forecasts at all. But then we ask, if we go next, yeah, we ask how bad is this bad? So is it like not usable at all, or how bad is it? So if you see that, if you just plot them on different scales, you actually see that the dagger has captured this variation that's coming up in the geomagnetic perturbations, but it has not captured the essential scaling required for the getting the correct magnitude of these perturbations. So maybe we are missing some context magnetospheric state. That's what is causing this issue. So go next. So maybe the current state of magnetosphere's context is missing, and that's what is causing this discrepancy. But then we can generate forecasts like this. So this is the data product that we have. So 30 minutes into the future, we can generate what the geometric perturbations will be like for by and large all locations on the Earth. And these forecasts are generated in like under a couple of seconds. So I think it's a second or two. So that's how fast these models are compared to conventional models. So there's a lot of tuning obviously that needs to be done. But if you go next, so what we have done is we have open sourced this whole model and in something called SpaceML. So I don't know if Lika ma'am would be talking about this, but SpaceML is basically a repository of a lot of ML based projects where our project is also uploaded. If you go next, you can go to our project and you can click on that collab link there. Go next. You can go 2 steps next, I think. Yeah, one more step next. Yeah, so if you open that collab, it will generate a Jupyter notebook for you. It's selected with the hardware, with the GPU anyway. And you can actually just run our code and get all of the plots that we have that you have generated for the paper. So in this way, we have a tutorial for you to how to use the model with the data. So, so we are hoping that these models are used further up to make them better. And you can go next, I think. That would be the last slide if I'm not wrong. Yeah. So some takeaways and some food for thought. You can use. So you can see that in the geometric perturbation case, we knew that this thing, the whole system exists on a sphere, and we put that constraint explicitly into the model. Whereas in the solar wind case, we sort of tried to understand why the model is generating some forecast. So one of the some food for thought is that how do we incorporate multi-viewpoint measurements and in a physically realistic manner? So for example, you have the stereo missions and let's say some AI data. How do you incorporate all of this data into an ML model when you know that these are at different spatial locations? And also, we have not generated uncertainties in whatever forecast we do. So can the machine say, I don't know? That's a field of research. So we'll see how things go. And I think we can have a discussion on that. So I think I'll stop there, and I'm very sorry for taking so much time, but thank you very much.
Hi, Vishal, this is nice talk. So I'm Sudeep from SESI. So I have one question. Can I ask?
Yeah, sure.
Yeah. So I find that you have in your slides somewhere you have shown that the mean activation values. So if I am not understood wrongly, um, so in that thing, I think your GradCam method, what you have actually explained in that, so that is only to highlight which portion of the your input images are actually taking part in the making the decisions. Is that right?
Yes, can think of it like
Yeah,
that.
okay.
Yes.
So this is only the GradCam method only is applied for the getting the interpretability of that thing, and
Yes.
in one slide I have found that you basically plotted some two scatter plots for different channels, where you have basically in the y-axis you basically plot something called mean activation values. So from where you are getting this mean activation value, basically is it something from the taking the amount of the important pixels which are found by this GradCam method, or what it is? Can you explain?
Yes. I went a bit fast there. So what I do is basically, so the GradCam is just giving us some numbers, right, all over the images. So I just take so in the slide number 16, I think I segment out the active region and Cornell holes. So what I do is inside the Cornell holes, I just sum up all of the active. I just take a mean of what the activation value is, and I do this for all the images that go into the model at different points in time. So the model takes a time series of inputs. So each image as a timestamp has these activation values. So it's basically just like like an area weighted thing. So just inside the Cornell holes, what is the average activation you have at a given time step across the whole data set? So that's basically the number that's put on the y-axis. So it doesn't really have any physical meaning right now, but it would be interesting to look at how to calibrate these activation values.
Okay. Yeah. Thanks, Vishal.
Yeah, sorry, Ankush, you had this question, right? Please go ahead.
Yeah, can you hear me, Vishal?
Yeah, I can hear you. Yeah.
Yeah, very nice talk actually. It's really needed to have some model forecast of solar wind and magnetic field at L1 based on solar inputs. So I have a question like you have taken a complete image for forecasting solar wind velocity, right? So, but actually high latitude regions may not be contributing what we observe at L1, right? So is it like if suppose just reduce the image, just considering the low latitude region which really map to the at L1 ecliptic plane and try to run forecast. Do you think they will be better?
That's possible. Yeah, we can do that actually. I didn't do it because so that is the
Because
thing, right? So I didn't want to put any of these constraints in the system at all. I just give it the full image and
right,
let it figure
yeah,
out.
that is good
So
to start with, of course.
yes,
Yeah.
yes. But
So
that's an
maybe
important
like
question.
because we
Yeah,
that data may not be relevant. Yeah.
exactly. So that's an
And second, I
important
have
point. Yeah. Go ahead.
Yeah, maybe. And second, I have like this about geomagnetic field variation. So have you used the solar wind data for this forecast? I missed maybe that point
Yes.
for
So we have
geomagnetic
used these.
perturbation.
Yes. So the focus is basically you have the solar wind measurements
Right.
just outside the OSHOC, and that's what we use to generate the forecast. Yes.
And what is like time history of inputs you are considering for that also?
So we consider 2 hours of data at 1 minute cadence for the solar wind
Okay, so
side,
past two
and
hours of
we
data to predict the at time t, right? That
yes.
is what.
So to wait 30 minutes later, and this prediction is also at 1 minute cadence. So geometric
1 minute
perturbations,
cadence.
yes, at 1 minute cadence. Yes.
Okay. Yeah, fine. Yeah, that's it. Thanks.
Yeah.
I think Vishal, you can hang around a bit and take questions in the chat box because we are running
Sure.
a little behind schedule. Thank you so much for such a great talk.
Yeah. Thank you.
Moving ahead, we are very happy to have Dr. Madhulika Guhathakurta among us today. So, Dr. Lika, please take over.
I believe this is going to be a recorded talk, right?
Yes, but she's around as well, so she can take questions.
Yeah, sure. That'll be great. So I suggest that
Yes, I
questions
am
are kept at
here.
Hey, Lika.
And you post the questions also. My internet is not great and I have noisy environment. So I'm generally going to mute myself and listen
All right.
for questions and look at the chat also.
Yeah, sorry for dragging you into this on a nice Hawaiian evening, probably.
Exactly. You owe
Yeah,
me.
I owe you.
And
That's right.
Vishal, that was great. I came in towards the tail end of your talk.
Thank you, ma'am. Thank you.
Good morning. Thank you very much for inviting me to give this talk at the Spark workshop at SESI, Kolkata, catalyzing academic and private partnerships in the use of big data for space exploration and human benefit. And in that context, the description of the Frontier Development Lab. Space has vast amount of data from decades of missions and the amazing opportunity to apply artificial intelligence and deep learning, in particular to that data in new ways. And there are really discoveries right before us that can be gleaned from that data that are beyond the capacity of our mammalian senses. So we established the Frontier Development Lab with NASA and the SETI Institute and leaders in commercial AI and commercial space to work on problems in space science, space exploration, but also challenges of relevant to all of us, all humankind. Now, AI has sometimes a bad rap. It's thought to be really artificial, a black box. But in my way of thinking, it is just augmented intelligence, much like telescopes augmented our vision, figuratively speaking, into the cosmos. And microscopes allowed us to probe deeper into human cells and everything else. AI ML enables machine capabilities in a similar sort of way to augment human intelligence, like autonomous navigation and coordination, bot automation, analysis of vast information sources, intelligent assistance, technology horizon scanning, anomaly alerts, voice-driven interfaces, and so much more that you're already living with and experiencing. Now, this is like a fun multidimensional GIF I like to show for many of my talks. We are at a point in our capability where we can train a neural net to learn to recognize a digitized thing with a high degree of probability. Just statistics. We can't see all of the data. I mean, that's the limitations of our human mammalian brain. We're looking for tool at multidimensional data level. And when we look at space data, that is actually absolutely amazing. And for that reason, I think I'm showing this movie. So it really gets interesting when you don't have training data or you're working with 3D or multidimensional data, which is what heliophysics or even space science data are all about. And so what is really interesting with this chip is once you have an inference model that is trained, it can take those random dots and you begin to see things, patterns, connections that humans can't with our limited mammal senses. And that's kind of the power of, I think, deep learning, machine learning. Now, there are a few reasons why deep learning and artificial intelligence fit so well in space science. One of them is space science is data heavy, petabytes of data. And as Andrew named, one of the leaders of AI pointed out, yeah, just keeps on pushing envelope to the right. With more data, and it gets accurate and happy. Now, when properly architected, right, efficacy of deep learning systems continue to improve with more data, long after statistical models have plateaued. Just like you can see the blue and red. Now, space science is also discovery heavy, just the data, and creative AI discovery of features and solutions becomes kind of important in that context. It literally is a domain where we are physically exploring frontiers. We are going places we have never been before. We are seeing things we have never seen before. We are collecting data we need to make sense of, and we need the discovery component of deep learning, the way it can figure out things for itself in a creative way. And that's kind of what really got me hooked into this area to begin with. Now, creative, is that too strong a word? let's use an example. So this is a six-legged robot designed to go over a rough terrain, perhaps better than a wheeled rover might do on, say, the surface of Mars. But if you don't want these poor people programming this whole concoction, how to move each limb of this robot, just have a DL model to let the robot figure it out for itself. In this case, this particular robot was given a very simple metric: go forward but touch the ground as little as possible, which is a pretty good proxy for efficiency. The gait will be efficient if you don't touch the ground with your feet more than you need to. Okay. It was set in motion, and initially it tended to be a little bit weird in its movement. The group went off to lunch and came back and found the system very proudly saying, I have achieved 100% efficiency. I'm not touching the ground with my feet at all. And so let me play this movie for you. And, you may laugh, and it is funny because it's like a kid. And that is the point, basically. There's no preconceptions, no bias, voracious appetite for data, astounding ability in terms of throughput to try billions of different combinations. That is the kind of supercharging we need to turn AI onto space science with phenomenal results. And it's on that basis that the NASA Frontier Development Lab idea was launched. And NASA has data, a lot of data. We gather approximately 2 gigabytes of data every 15 seconds from over 100 currently active missions. We do this every hour, every day, every year, and the collection rate is growing exponentially. Handling, sorting, and managing this data is a massive challenge. Our data is actually one of our most valuable assets, and its strategic importance in our research and science is really huge. So now, what if AI meets science? We just got started. It's planetary defense, space resources, space weather, exoplanets, astrobiology. There's a lot of science to be covered in the Science Mission Directorate. And this is where Frontier Development Lab is born. So we established FDL with NASA and the SETI Institute and leaders in commercial AI and commercial space. And we are now witnessing an inflection point where AI promises to become a tool for discovery with the ability to process vast amount of data collected over time, allows us to visit the physics-based model of the past to better understand underlying principles and radically improve time to insight. Deep learning means deep science plus public-private partnership and what's new synergies for NASA research. Now, why partner with Silicon Valley? Well, very clearly, GPU powered is stripping Moore's law, better scale era of data. Remember, algorithm development is only about 5% of tasks. You still have to get the compute capability. Developing inference models is costly. FDL gets a significant amount of resources from the commercial partners like Google, Intel, and others. And that's really, really important to create this public-private partnership, because no agency has that kind of capacity. Little bit of history about Frontier Development Lab. It was launched in 2016. Fdl is an AI machine learning research accelerator established in partnership with the SETI institution and in collaboration with academic and private industry. Now, in its 7th year, the Fdl program has been successfully addressing really some of the core goals of what AI ML can do, and some of the presidential executive order guidelines in the US. Why FDL? AI is evolving quickly. The revolution was started by the application of neural nets to large quantities of pre-labeled data known as supervised deep learning in 2012. These methods now are more or less mainstream. The state of the art is now looking towards sparse or unlabeled data known as unsupervised deep learning or machine learning, and how to explain the uncertainty of the results. This is known as explainability, and a key part of determining really the veracity and usefulness of any AI tool. And although deep learning is being democratized today, producing excellence, meaning explainable, bias-free, and trustworthy results, is increasingly difficult, requiring multifaceted, sophisticated teams and a deep understanding of how to use the newest techniques. This is where FDL provides unique value and opportunity for space science and exploration, really. And as you can see, sort of the horizon of these activities, right? And deep learning Big Bang is around 2012. FDL was conceptually initiated in 2015, and that horizon basically continues. And why a dedicated lab? Let's go a little bit deeper into it. ML is expensive. Data scientists at PhD level are difficult to recruit, and average salaries are 140K US dollars per year. That's on the lower side almost. Market rate for seniors is $1 million or more. Moreover, compute costs basically limit the experimentation and ambition that we have to utilize our data. Number two, ML has large failure rate. Data scientists are following for typical project failure, not knowing the data, poor management, lack of good questions. Now keep that in mind, lack of good questions. Not every topic is suitable for this application. Number three, the unsupervised learning gap. AI tools have been maturing quickly, and most scientists are now familiar with the basic get results with off-the-shelf tools using well-tagged data. That's the supervised content we're talking about. FDL's team approach allows teams to tackle far more sophisticated AI workflows. Fourth, the explainability gap. Similarly, while it may be possible to develop a compelling demo, ML often fails in the real world due to procedural errors, unintended variables and biases, understanding what works and why is key. These are kind of why we really need something like a dedicated lab. Now, what does FDL bring into the partners contributing at all levels? High-end compute, GPU, CPU resources, software, and advanced AI/ML algorithms, team mentors, subject matter expertise, speakers, facilities, and funding. And the curve here basically shows, the word of on the lower left-hand corner, supervised learning. That's the democratized, AI approach that communities are beginning to practice. And where we want to go is towards the upper right-hand corner to increase capacity and explainability, and we're kind of trying to bridge this gap. Another way of describing, right? What is FDL looking for? Why is this lab approach valuable? Because we're looking for problems that require innovation in data pipelines, training, problems that use very large data sets, which requires significant training and engineering costs, which is time and capital. Problems that require integration of numerous AI tools to create AI workflows. Now, these are not things that academic institutions routinely handle, but the commercial AI sector do. Problems that require high degree of confidence in the outcome. Problems that have sparse or dynamic data or require transformed learning. So you can see, and again, we are going from the democratized AO on the lower left-hand corner, which is simple data workflows, static data, low cost, to the upper right-hand corner of complex AI stacks that requires data pipeline innovation or large compute. And on the lower axis, you are basically going through available AI tools containers to emerging AI techniques to the unsupervised world where we can make the headway and also discovery class science. Now this I call the FDL event time horizon. FDL has a dedicated and passionate partner community aligned behind a common vision for AI for science and space exploration for all humankind. And since its inception, you can see what the growth has been for integrating academic institution, private sector, and government agencies. And the newest in this bucket in 2020 is U.S. Department of Energy. The partnership is structured where SETI Institute facilitates public-private partnership by acting as a hub between space agency, academic, and commercial partners. And then Trillium Tech, subcontractor to Trillium Technologies, manages most of the commercial, academic, and space agency partners, and the FDL faculty and runs and coordinates FDL throughout the year. And you need every component on this chart to make FDL what it is today. So how FDL works? Basically, FDL tackles knowledge gaps in space science by pairing machine learning experts with heliophysics, astrophysics, astrobiology, earth science, and planetary science researchers for an intensive 8-week research sprint held in the summer break of the academic year, although the journey from challenge definition through to finish result takes 1 year. Interdisciplinary 4-person teams of PhD and postdoc level researchers address tightly defined science challenges that are informed by knowledge of what's possible in ML, as I said before, very important. Mentors who are subject matter experts provide support to the teams and drive research quality. external and partner experts, special guests, and visits to partner labs contribute to the larger understanding of the problem and provide a community of expertise that drives excellence. FDL's format encourages rapid iteration and prototyping to create output full application to the space program with substantial compute resources provided by FDL's commercial partners. Remember that this is where experimentation happens and for which we need really substantial compute resources. This combination of curated challenges, close mentorship, community of expertise, and an emphasis on rapid prototyping has ensured a really high success rate for FDL. As such, FDL has demonstrated how structured, interdisciplinary problem solving, radical collaboration methods, and partnering with commercial organizations with relevant expertise can be useful to NASA's science and technology. And it's not just NASA's, anybody who's interested in adopting this. So now let me kind of quickly talk a little bit about things we have done. So here, what you are see is the physics systems observatory to give you a sense of the heterogeneous data. We have 20 operating missions with 27 spacecraft crisscrossing the distance from Sun to Earth and all the way to interstellar medium, and that's kind of providing us with our data. In addition to the NASA missions used in research for space weather, the heliophysics split you saw, there are additional missions operated by NOAA used for space weather forecast. This visualization presents orbits of the current heliophysics satellites covering the space near Earth, all the way to the Sun or branch point L1, to which, Aditya L1 will be joining soon. And finally, a view of the current missions operating in the inner solar system. This visualization presents orbits of the current heliophysics satellite covering the space near Earth, basically, as I was mentioning, and it is a growing pool of resources. Let's talk a little bit about the scale of data, the total data volume over projected mission lifetime. There's currently over 8.7 petabytes of compressed AIA images and products. Uncompressed, this would expand to over 20 petabytes. Optimized, solid state device reading at 7,000 megabits per second would take over 14 days to read through all AIA files, and many of you use this. Real-world read-write speeds are closer to 500 MB per second, or more than 200 days. Now remember, size isn't the only issue. There are over 240 million AIA images. If you look at the stereo SECI-A, that's about 38 terabytes, SECI-P, 29 terabytes, EIT, 5.5 terabytes. The variety of data and volume of archive has driven a rise to what we call data science today. So this is kind of the scale of data, at least we are utilizing in heliophysics. Now, this is just what we have done over the past 5 years. NASA Heliophysics has been the primary investor in the first few years to begin with in the frontier development lab. Now, and what you are seeing basically, all of our different partners from the private sector, Lockheed, IBM, Intel, NVIDIA, Google, as I had showed in the event horizon chart, we have done now over, this is a little old slide at least 17, 18 ML projects in Helio. On the right-hand side, what you are seeing are the different kinds of problems we have undertaken. The integration of physics and explainability is really allowing AI to become a powerful tool for discovery. And I'm going to go over some of these topics very quickly. Super Resolve, for example, is an example of workflow optimization, which is cost and time savings and results in enhanced data product. 50 years of solar magnetic field data. Create virtual instruments is an example of forecasting and prediction. Create virtual instrument prediction of extreme ultraviolet irradiance, enabling virtualization of SDO instruments. Make forecasts is an application of applying decision intelligence with rapid assessment, improved strategic decision, prediction of GNSS disruption in 1 hour in advance, or extract insight from noise is an example of anomaly detection, mapping star spots hidden in test data. Auto-calibrate. Cross-calibrate is an example of autonomous systems with onboard AI auto-calibration, resulting in resource efficiency with auto-calibration SDO. Now, this is a super resolution map of the solar magnetic field covering 40 years of space weather events, one of the examples. The challenge was to create a homogeneous set of magnetograms. Now, numerous observations have monitored the sun's magnetic field over the last 50 years with high level of inhomogeneity, reducing their effective value for understanding long-term variability in the approach. Apply machine learning for calibration and super resolution. So the question was, can we calibrate and super resolve historical observations of the solar magnetic field, taking into account these inhomogeneities such as resolution, noise, and saturation level, both from ground-based and space-based data. The ML pipeline cross-calibrated and upsampled data from older instruments like SOHO MDI to create a homogeneous observational baseline with newer SDO HMI, thus creating super resolved image of the sun's solar magnetic field upscaled to contemporary instrument. And that's what you're seeing. You're seeing input, which is SOHO MDI, target, which is SDO HMI, and ML output that is definitely much more resolved, compared to what the input was. The next question was, can we auto-calibrate in-space instruments without sounding rockets, for example? And by using a prepared AI-ready SDO dataset that we just created earlier FDL topic, this challenge aimed to transform essentially AIA data into extreme ultraviolet images. Using 4 years of 7 cotemporal UV channels from SDA AIA, the team successfully developed an auto-calibration model for UV images from AIA. And this technique can be adapted to other imaging or spectral instruments operating at other wavelengths. So the top row, it's an overview of the degradation of helium-304 channel. It's recovered images and the architecture used is below. In the bottom row, what you see is comparison of real 211 angstrom channel and synthetic 211 channel. So actual and ML calibrated, where you can't even tell the difference. This is fascinating and has tremendous implication for future. So expanding the capabilities of SDO, the team devised a way for solar extreme UV telescope to self-calibrate, improving our capability to monitor space weather. Furthermore, the team created a synthetic telescope to image the sun's corona. These techniques enhance the scientific return of space missions and basically paves the way for an autonomous space weather constellation where we don't have to fly every filter. We can create synthetic data. This is, something that was really pretty awesome back in 2018. So Solar Dynamics Observatory Malfunction, one of the sensors on the EVE experiment, makes a malfunction in 2014. And MIX-A really provides the spectral irradiance that is the component of the irradiance spectrum that energizes the ionosphere. It's a very important component. So an overview of the ML architecture with the SDO input is on the left, and output, which is the MIX-A spectral irradiance, which we actually lost in 2014, is on the right. Machine learning is used to compare how the sensor's past readings lined up with measurements from the observatory's other sensors, and then estimated what it would record where it's still running. It's a bold question to ask. The team's approach for nowcasting MIX-A spectral irradiance measurements from AIA images achieved a median error of 1.6% across MIX-A spectral lines, outperforming a number of approaches, including a differential emission measure-based approach, which is a physics-based approach. Now, with the machine learning dataset prepared from SDO, there are derivative outcomes. This is the SDO ML concept. Okay. So, using the same dataset, this project identified spatial patterns on the sun to determine the calibration factor that corrected for SDO UV instrument degradation, which would help to avoid the cost of regular suborbital launches to obtain calibration data, especially for future missions, because ultraviolet UV sensors actually degrade over time, and our the lens of our eyes degrade with age. So on top row, you have an overview of the degradation again of 3 or 4 channel. It's recovered images and the architecture used. And the bottom row already that I showed you, the 211 channel, real and synthetic. Now you have this product created already. Now the derivative outcome is that you can now take this energy input and create essentially thermospheric density prediction. The same SDO ML data and ML techniques can be leveraged to construct the thermospheric density models that outperform the current state of the art, both in accuracy and computational speed, while also providing uncertainty estimates of the predicted quantities. And this is really important, especially if you paid attention to what happened to Starlink satellite in early February. They were launched, I think SpaceX launched about 48 of those, and 38 of those Starlink satellites didn't make orbit. And essentially due to what was happening in the thermospheric density because of what happened on the sun. Anyway, the team used machine learning and solar activity data to improve orbital drag estimation. Comparison of thermospheric density modeling between the solar drag model and one of the NRL model. Actually, this particular output from ML outperforms that. Let's talk about origin of solar wind, right? I mean, with Parker Solar Probe getting closer and closer with each new perihelion to the sun. So the question was, can AI help us find the complex structures in the solar wind? And the closer we get, the more complex it is getting. ML can learn to find, organize, and classify complex structures in the solar wind to advance our understanding of the fundamental building blocks that make up the magnetic field of the solar wind at different points in space. For example, the top panel shows from left to right, kind of look at those structures. Interplanetary coronal mass ejection, first detection 1971. Interplanetary magnetic field enhancements for detection 1983. Switchback, first detection 2019 with Copper Solar Probe. And so the question now is what's next? The pipeline is able to identify distinctive features and group similar time series into recognizable patterns using only 3 million operations instead of the 90 trillion from the traditional picture. The findings basically reveals multiple clusters of solar magnetic field structure. So this is kind of really opening Pandora's box and asking these questions as we gather more and data. How do we go about really assessing this clustering? Yet another approach, star spots and the rotation rate of stars. So the question was, what can we learn about heliophysics from stars? Telescopes like Kepler and TESS measure brightness over time on single pixels for stars light years away. Now, ML can learn from faint star light observations to plain luminosity dips through compelling plausible hypotheses in terms of extrasolar transits, spot formation, and the rotational characteristics of each star. So the pipeline starry spotter transforms Kepler light curves into images, stacks them, and applies computer vision to extract star spots properties. So these are, I'm just going through this very fast, sorry. When Apollo 8 astronauts came back to Earth, astronaut Bill Anders famously said, "We came all this way to explore the moon, but on the way discovered Earth." In FDL Europe, Isa asked, "Can we use AI to tackle challenges here on Earth?" And here's a movie I'd like to play for you. And so, floods are deadly, destructive, and costly. You know that. It's a greater share than any other type of natural disaster. In the US, floods cause 140 deaths on average each year. Globally, flooding causes economic losses of more than 250 billion per year. So USGS asks the questions where, how deep, and when flood occurs. And so the team took two questions of USGS, where and when, and build a model of higher accuracy than the ones in use today, so that there is fewer false positives and fewer false negatives overall. In this case, false positives are bad because that is when you are predicting that there will be flood, but there is not one. And they are bad because over time people can start to ignore evacuation and warnings. False negatives are bad too. You predict there will not be a flood, but in fact there is one, and then you lost the opportunity to give people early warning for evacuation. So this is sort of the current approach. This is physics-based modeling. This is what NOAA USGA they are doing, and what gap needs to be filled. The model also has to carefully account for human-altered waterways such as dams and levees, which is difficult and time-consuming as well. So let's talk about the FDL co-innovation here. The domain experts brought the knowledge of data that would be predictive of floods, like accumulated rainfall data, satellite imagery on land use, and topography, and river basin characteristics, things like vegetation or impervious surface area or soil type that tell us something about how fast water can drain into soil. This is that interdisciplinary team. They also brought with them knowledge of a data set that would give us the label. Very important. Stream gauge measures water level and water flow, and that can give us labels, flood or not flood. USGS maintains over 10,000 of these stream gauges across the country. PRISM is combination of radar and ground measurement in communication with project partners, selected a set of data sources that are publicly available and predictive of floods. And they integrated 8 data sets for this project, which is just a starting point. A stream gauge, as I mentioned, measures water level and water flow, and that can give us labels, flood or not flood, and that you're seeing this 10,000 steam gauges across the country. Steam gauge network is extensive. Water levels reported every 15 minutes. Now the technology experts, they brought understanding and knowledge of different machine learning models that would fit for the job, for those of you who are curious. It was multi-layer perceptron, CNN, gradient-boosted decision trees, and random forests that this team utilized. And so the question was where flood occurs, right? It's improved accuracy. The result that these teams were able to achieve in just 8 weeks was incredible. They were able to build models that improved the accuracy of both of the 2 questions, where and when. This is the where question. For a specific gauge location for a given month, can we predict whether there will be a flood that month, whether we cross the flood threshold as defined by NOAA? These are important questions. They also predicted accuracy of the when. And really, given the rainfall, they were able to predict peak arrival time of flood, provide another early warning system. 10,000 does not cover the entire US, and it does not even touch the issue globally, but this is progress. And yes, of course, there are suggested ways to improve in the future, but because of lack of time, let me just move on. How can AI help us return to the moon? Yet another question. We just celebrated 50th anniversary of Apollo 11, and now with the Artemis program, NASA is leading us into the next era of exploration with plans to put a man and the first woman on the moon relatively soon. And of course, now we are heading back to the moon to stay, a long-term permanent. To achieve this monumental feat, we need to look for resources on the lunar surface. Expensive to send resources to send to the moon from Earth, right? So look for what is available on the moon, and metal is like a key component. Metal is a key resource required for lunar base, and matter can actually be deposited in the form of metal meteorite. This is an iron nickel meteorite found in the Curiosity rover on the surface of Mars, and similar meteorites have been found on Earth. So finding a way to detect this metal on the lunar surface would be a significant step forward in our goal of making a sustainable base on the moon. Now this is the moon crater called Tycho on the near side of the moon. It is 80 kilometers across, and here is Golden Gate Bridge. For perspective, really 5 kilometers deeper than Mount Whitney. Can't distinguish between metal or a rock on the surface, so we need more information basically. And so then enters the world of data fusion when we need more data. So to solve the problems, the team created 6 different data sets from international missions, creating a big data set, including 12 instruments that cover different aspects of the electromagnetic spectrum: visible, UV, microwave, gravity, magnetic, and thermal. Combine this with elevation imagery that gives info to provide relief of the moon, terrain of the lunar surface. Blue indicates low elevation, and brown is high. So I'm just quickly kind of go through some of these overlay data, as I mentioned. And I already described, right? Also use rock abundance, where red is rock ridges, blue is smooth. Use surface temperature, red, yellow, hot, blue, green, cold areas. Use surface temperature, again, red, yellow, hot, blue, green, cold areas. 20, combining all these data sets. By using them, we can really create a data set that is powerful in a technique for anomaly detection on the moon, to find metal signatures without knowing what the signatures are. And so this is what you see here. By combining all this data, by fusing them, we created the synthetic data to find metal signatures, use computing power to look for general patterns, and focus on optical, thermal, and magnetic properties of the data most closely. Isolated 7 distinct patterns in the data, each relating to some anomaly, meaning a bright area or strong in magnetic field. And no one has found metal on the moon. Okay. Why is it important to collect infrared and magnetic data? One specific way we think we can detect metal is to look at the temperature of them. Metals are good at absorbing heat. We think same thing happens on the moon, basically. So we expect to see variation of the temperature through the lunar day from their surroundings. The team provided 45 terabytes of existing data and analyzed them and trained them to detect these kind of anomalies. It's a little bit of detective work, and generated AI maps whether there might be these types of thermal anomalies. That's what you're looking at. Metals are very good at absorbing heat, essentially, and we have figured out a way to extract them. Now remember, these are still early stages of utilizing the data in this 8-week time period. Very quickly, this is really giving you the AI portfolio that the FDL has undertaken over the last 7 years, and you can find all kinds of science activities, decision intelligence, anomaly detection, optimized workflow, the combination of utilitarian AI approach and discovery AI. these are actually some of the ML achievements in FDL, some of which I just showed, like star spot. Geo effectiveness is a paper that just came out by one of the speakers from as the first author from this panel, and many others. And similarly, in 2021, I showed you something about the origin of the solar wind and solar drag, and many other disciplines included. Space ML is kind of FDL's way of doing the open science initiative that NASA is engaged in, making all these data products available to the community. Please go to the frontierdevelopmentlab.org and start utilizing this and send your comments to the team members. So ultimately, I would say that interdisciplinary is absolutely key. Data scientists don't know the pitfalls, domain scientists don't know the full toolbox. The AI toolbox is already too broad and deep for most scientists. Similarly, it's hard to know the tools unless you have a deep familiarity with the problem, so you bring them together. And finally, this is the FDL formula. FDL was born as an applied research accelerator for AI, which in 2015 we call data sciences, where we are bringing research talent, challenge plus data, and capital plus capacity through government agencies, academic institutions, and public-private partnership. It is a culture of anything is possible. Thank you.
Thank you, Madhurika. That was a wonderful exposition of FDL. Would you be able to take questions, or should you just type some stuff in the chat box if you have any questions?
Yeah, I have my microphone open.
Okay, all right. So one question that I had is this FDL has been such a wonderful exercise, which is not just been impactful in the US, but as we saw from the first talk today by Vishal Benjamin, it has also impacted students in various parts of the world, including India, and they have also in fact contributed to these projects in a very meaningful way. Is there a scope for implementing an initiative like this in, for example, let's say India, where we have quite a bit of interest in machine learning, we have various people interested in software. Of course, the data that we keep has not been managed in such a good way as has been in the US, and for problems which are relevant for the nation, you do need to have a large repository of data. For example, you talked about floods, you talked about identification of disasters, which are very pertinent problems for developing nations like India, right? So if you could, if you could implement something like this in India, it will not be just useful for space sciences, but also problems which are locally relevant. What are your thoughts on doing something like this in India?
I think that, I have in a way already started that discussion. And the reason, even though I know that your workshop is more focused towards solar physics, I wanted to give the powerful examples of other disciplines. And I think in the world of earth science, when you're looking at flood, wildfire, drought, and the amount of data that India has, I mean, something like this is absolutely necessary. And there might be aspects of it going on in places that we do not know because we don't belong to the earth science community in India. But there is a sense of, really supporting Indo-US collaboration in science and data science, including AI ML. So I think organizations like IUSSTF perhaps, or other academic institutions like yours, and Indian Space Research Organization. I mean, there are many entities in India and in US where we could come together to form, a larger collaboration. So FDL has, it's not quite a franchise really, but there is a very strong FDL Europe component, for example, right? The management skill that this team brings is very, very important, something that we are not able to quite reproduce the same way in academic institutions, because we are dealing with um, data tools that require constant upgrading, validation, and compute resources. So I think it's a very important topic. It's an important question you're asking. It's matter of political will between countries and resources, and also academic institutions and agencies to carry this forward. I really would like to see something like this happen in India, where we can co-share basically, right? I mean, I know Vishal had to spend, nights awake in order to do the virtual FDL last year. So there are, early career researchers from all over the world who are participating in this.
Right. I guess this year's edition is going on right now. My first PhD student, Andres, who's now apparently an instructor at FDL, is going to be there for the next 3 weeks, I guess.
Yeah, I was in fact there for the first 3 days and
Okay.
then came to Hawaii for the other meeting. And this year we have also integrated Department of Energy. And the topics are brilliant, and the students kind of gave their first uh, really first description of the project they are tackling at the end of 1 week. It is something, it's, for me, it's a marvel to witness, how we construct these challenges and how they really so powerfully come together, bringing together students who have never known each other before.
All right. I think there's a question from Ankush Bhaskar in the chat box. He's asking, is the team for each project in FDL limited to four people only, or is it could it be larger?
So typically that's kind of where we have started. It's optimized to 4. That seems to be the right number. So as I say, there is actually a lot of management behind this. It is not just a typical academic institution project. Uh, but that doesn't mean that you can't bring people to get them trained, etc. But 4 seems to be the most efficient number of people working on a topic. So 2 in domain scientists, 2 in the computer AI world, and then there are 2 mentors. And then there is a host of subject matter experts. So this is actually a curated process. At the end of first week, they just gave their first presentation on Friday, just 10 minutes to describe the problem. At the end of 3 weeks, there is actually a go no go decision made, where you bring external subject matter experts and you are trying to express and demonstrate your problem to them. And at that point, you might have to revector your problem, because what you thought you could do, maybe the data didn't show up, or maybe it just seems like an intractable problem. So they are coached, guided, but they are working on this, and that traditionally has worked pretty well. But beyond that, we can experiment with lots of ideas.
Okay. So I guess, Yoshita, do you have any more questions from YouTube, or we're good to go?
No, I think we are good to go. So, yeah, so next talk is Dibyendu Nandis, as we could not complete it yesterday because of some technical issues. Dian, please take over. And yeah, we intend to finish this session by 12:45, so you can tailor your talk accordingly.
12:45, it's 12:28. Are you kidding me?
Yeah, I mean, of course, 5-10 minutes
No,
extra, but
no, it's not going to happen, right? It's a 40-minute talk. It's 12:30 now, so there is no way we're going to finish it before 1 o'clock. So before I start, Modulika, thank you very much. We really ate into your dinner time, I guess, in Hawaii. But thanks for coming in. Okay, let me share my screen. Okay, so I hope you can see me, you can hear me, and you can see the screen. Is it full screen now?
yes, it's full screen and we can see it.
And it's moving forward, right?
Yes, yes, it is.
All right, so I will move very quickly to the first part of the talk. I really intend to go into the physics of space weather. And I did manage to give you a bit of a motivation of why I talk about the physics of space weather, which nobody else is covering in this conference. And so I'm not going to repeat that. And I guess all of you know by now what is SESI, where I come from. So I'm not going to repeat any of this. I will just go into say that the space weather is actually very important for us from various perspectives, including the technological perspective, because it impacts various space and ground-based technologies, starting from satellite operations, mission lifetime planning, because satellite drag and its lifetime is dependent on space weather. Satellite-based communications, high-frequency radio communications, GPS navigational networks are all affected by the variable environment in space. At ground level, electric power grids, oil pipelines, and some people believe internet cables, which essentially are large conductors, are also affected by geomagnetic storms, which are induced by space weather, which basically follows from Maxwell's equations. If you have a variable magnetic field, you induce large currents, and this can trip power grids and are hazardous to oil pipelines in the northern latitudes, where the impact of geomagnetic fields are felt much more than at low latitudes. And as I will also argue, space weather is important for planetary atmospheres and the long-term evolution of planetary environments which determine habitability, and therefore it's important from various perspectives to look at our variable and changing space environment. I did talk about the climate part a bit yesterday, so I think this is where I got cut off, where I was talking about how do we explore space weather. So one of the ways that we explore space weather is, of course, through observations and collection of data. And most of the talks that you've had until now have been talks about mining data. So essentially, we need to collect a large number of observations of the solar system, starting from solar activity to its manifestation near Earth, to be able to understand and constrain what is going on in terms of the origin of space weather and its impact on our space environment. Agencies like NASA, ESA, and the Japanese Space Agency have been far ahead of other agencies in terms of exploring the sun. NASA certainly has had many missions, and we know now that our understanding of this variable space environment has really been revolutionized in the last 30 years from this multitude of satellites that have been up in space over the last couple of decades, and there have been more than, I think, 30 satellites studying the solar system. India's first solar observatory, the Aditya L1 mission, is going to be launched within the year. And this is going to be a great observatory, implying it is going to have multiple different instruments to look at the genesis of solar um, radiative variability. How does this UV radiation, how does it X-ray output vary? It's going to look at the genesis of flares. It's going to look at the origin of coronal mass ejections and diagnose the sun's corona. It's going to look at the kinematics or the propagation of CMEs through the inner heliosphere, through the solar system, in order to be able to understand their dynamics and also provide important clues in predicting their arrival times. Other than these imaging instruments, it also has certain instruments to measure the properties of the in situ plasma, or the local plasma at Lagrange point L1, while the solar wind or solar storms are propagating through that location in space. And this provides not much, but a little bit of advance warning for the kind of space weather that Earth or the Earth's magnetosphere is going to encounter. More importantly, more than the advance warning here, we are looking at this data from the perspective of being able to establish causality across the solar system, starting from an origin of a solar event at the sun to its impact at Earth. I think Dipankar will be speaking in more details about the Aditya mission sometime, I think, somewhere in the program. All right, so understanding and forecasting solar activity is therefore important in order to be able to assess its impact on our space environment. And this implies understanding the origin of solar magnetic fields, solar storms, the changing solar wind conditions, which Vishal was talking about earlier today, predicting the occurrence of solar flares and solar storms, including solar energetic particles which are associated with solar flares, high energy radiation, which are also associated with solar flares, and eventually the planetary and technological impacts. And all of that begins with magnetic fields in the sun. And what I would like to give you, leave you with in this lecture is an understanding of the physical mechanisms or physical processes that are at work both in the interior as well as in the exterior of the sun, which eventually manifests as space weather, and also talk a little bit about its impacts on planetary atmospheres. Okay, if you want to do that, we are really moving through multiple different domains. A domain of the interior of stars, where the plasma beta parameter, which is the gas ratio of the gas pressure to the magnetic pressure, is pretty high, implying the gas or the plasma dominates the dynamics, to the solar corona or outer atmosphere, where plasma beta parameter is low, implying it is the magnetic field which dominates the dynamics of the coronal plasma. And then when you go beyond the Alfvén surface, out into the solar wind becomes supersonic, so its dynamic pressure increases. And then we are in the high beta plasma regime again, which is what is manifest with the impact of stellar winds and stellar storms on planetary magnetospheres like that of Earth. So a physical understanding of this domain implies understanding different and diverse processes that are at work in the sun's interior, in the sun's corona, and in the solar wind and near planetary environments. Okay, let's look at the fundamental physics of the generation of magnetic fields first. So stars like the sun are sustained by nuclear fusion reactions, which generate enough temperature to ionize the matter, and therefore the matter exists in a completely ionized state, or the plasma state, in the interior of stars. In the inner part, when nuclear fusion generates energy, from there until the top of the radiation zone, energy is transported by multiple absorption and re-radiation of photons. Following that, there is a layer of plasma that becomes opaque to the radiation, and therefore this absorbs the energy from the photons gets heated up and move up to the surface where it radiates the excess heat. And this is what you see as photons or light from stars. Then it cools down and becomes denser and sinks again, giving rise to convection in the outer 30 layers of a sun-like star. And this is known as the convection zone. So you have ionized matter, plasma, and then you have their motion. And this is where, therefore, the field of magnetohydrodynamics or the dynamics of magnetized plasmas come into effect, because you have plasma motions which whose energy you can tap into to produce magnetic fields. So one can look at the Maxwell's equations, and from there, under certain approximations of non-relativistic plasma and a neutral plasma, overall neutral plasma, drop off the Poisson's equation and the displacement current, and then eliminate the electric field by utilizing the Ohm's law for a conducting plasma. And by doing that, you end up with an equation which is known as the magnetic field induction equation, which is noted down here, which tells you how the magnetic field B in any domain, plasma domain, evolves as a function. If you can solve it, integrate that will tell you how the magnetic field evolves as a function of time in space, given a plasma velocity v and a turbulent diffusivity of the plasma eta. And of course, you have to satisfy the equation divergence of P is equal to 0, which is the solenoidal condition, which implies that flux is sort of conserved. Now, recall that you have this velocity term v sitting here, which implies that for a full description of the system, you must also have a dynamical equation which tells you how the velocity evolves in the interior or the exterior of stars, and for which you need the Navier-Stokes equation. So to see here now is the freed Navier-Stokes equation without the magnetic terms there, which is really an equation which expresses the conservation of momentum. And if you can solve this equation, then that gives you the evolution of the velocity v as a function of time in space. And of course, this is easier said than done, as this is a very difficult equation to deal with. When you are dealing with plasma in the domain of magnetohydrodynamics or MHD, the magnetic terms also become important and contributes a magnetic pressure to the overall pressure, and a magnetic tension term, which really is a term which tells you that magnetic fields doesn't like to be deformed by plasma flows. So essentially, this term really fits back onto the velocities, right? So both these terms, in fact, because the pressure gradients are what drives velocity flows. And then if you have a feedback term where strong magnetic fields feeds back and quenches the flows, that's a feedback mechanism or a nonlinear mechanism. And of course, then you have V sitting in the evolution equations of the magnetic field. So these are coupled equations, and your life is starting to get complicated. And of course, it gets more complicated when you realize that convection is of thermal origin, and this is of course also driven by the heat flux. And this is encapsulated in the energy conservation equation, which you must also then solve and put it in the whole cauldron to try and figure out what's going on in the full system in the interior of stars. This term Q here, which is the source term, in MHD systems, for example, in the corona, also imbibes the effect of ohmic dissipation or Joule heating, which allows you to convert magnetic energy to thermal energy. And so that process of magnetic reconnection and magnetic dissipation is an important source of heat in this equation in MHD domains where you can sustain magnetic dissipation. Along with that, you have to also have mass conservation in any fluid system. And this is simply the continuity equation, which you are well aware of, I suppose. For a plasma system, you can break it up into into a conservation of electronic charges and for example, ions and electrons separately, because your overall system is anyway neutral. But overall, in a single fluid plasma, you can just deal with the continuity equation, which tells you how flows evolve, constrained by mass conservation. Okay, there's certain assumptions that one needs to worry about and keep in mind to apply the concepts of MHD or magnetohydrodynamics in the solar interior or even on the surface, in its exterior, and also in the solar wind. So the conditions are that the collisional frequency of the plasma must be much smaller compared to the plasma frequency. The plasma must be a continuum, implying that the length scale of the system that you're studying, or at least the processes, are happening over a length scale which is much larger than the ion gyro radius. What this implies is you don't see individual charges in motion, and this is actually coupled with this single fluid assumption, where if your length scale of the system is much larger than the device length, then effectively you are not seeing any single charges and you are overall seeing a single fluid. And this helps you in dealing with the situation of this plasma, which really is constituted of ions and electrons, as a single fluid, allowing you to apply the concepts of fluid dynamics in a plasma system. We also assume that the plasma has to be in thermodynamic equilibrium, at least local thermodynamic equilibrium, which implies that the time scale of interest must be much larger than the collisional time scales, or the length scale of interest, which over which your physical processes are happening, are much larger than the mean free path, which allows the plasma, at least locally, to attain thermodynamic equilibrium, so that you can describe the plasma in terms of the extensive global parameters like pressure and temperature and their meaning. I will not spend much time over the concept of device length, but this is something that is very important for us to understand who deal with MHD or plasma physics, because this sort of differentiates the domains of MHD from the kinetic domain. So what happens is, when you have in a highly conducting plasma, when you have an ion or unbalanced charge locally, you have a cloud of electrons which surround it, and this sort of neutralizes the impact of this ion and limits it to a radius which is roughly the radius of the electron cloud, and the net impact of that is the potential falls off much faster than the typical Coulomb potential due to device shielding. And this sort of results in effectively shielding out the impact of a charge beyond the device length. And if you can actually make estimates of the device length in the interior of stars as well as in the outer atmosphere. So the interior, for example, the device length is 10 to the minus 11 meters. This is important, which implies that as long as you're a few times over 10 to the minus 11 meters, you're dealing with a system larger than this, your description of MHD is fine. You can get away with the MHD description system. For the solar wind, that's much larger because collisions are very infrequent. The density of plasma is very low, so you're looking at 10 meters for the device length in the sun's outer regions in the solar wind, and so you must be over much larger scales of few kilometers at least to be able to describe the system as an MHD system. When you're reaching scales close to 10 meters, like 100 meters or so, you're really reaching the kinetic scale where you should look at the motions of individual ions and electrons rather than treating the whole system as a single fluid. So these are important things to keep in mind when you're trying to model this Sun-Earth system. So the full set of MHD equations constitute of all these different equations which you must solve simultaneously. We don't always end up doing that, because what happens is one of the most complex equations here, the Navier-Stokes equation, which describes the velocity flows. You can essentially observe the velocity flows in the sun and incorporate that into your magnetic induction equation, and then solve for the magnetic field only in the kinematic regime, and therefore get rid of this sort of nonlinearities in the system. And that allows you to build more simpler models. But if you have the computing power, you can solve all the 5 different equations simultaneously and do direct numerical simulations to figure out how the velocity and the temperature and the magnetic fields all evolve simultaneously. So let me talk a little bit about the magnetic induction equation and why is it easy for astrophysical systems to generate magnetic fields which is at the heart of space weather. So if you don't worry about the first term and just look at the second term, then you get what is known as just the diffusion equation, right? Where your magnetic fields, any initial magnetic field will decay away over a typical time scale, diffusion time scale given by L squared by eta. So obviously then the first term is important in terms of being able to generate a sustained magnetic fields. So one can take the ratio of the first term to the second term in terms of some of the numbers that are associated with the system. And then you get the number which is known as the magnetic Reynolds number, which is a product of the velocity and length scale of the system and divided by the diffusivity of the system. Now you can imagine that in astrophysical systems, the length scales and the velocities are typically very large. This implies that you can produce a sustained magnetic fields against dissipation in these very large systems, whereas it's very difficult to do so in small plasma systems that we encounter in the laboratory. And therefore the sun, which is a very large system, can very easily generate magnetic fields and sustain it against dissipation. In the ideal MHD limit, where you can completely, let's say, assume that your diffusivity is negligible, you can reduce the induction equation to only the first term. And then you can show actually that for any arbitrary vector f, which satisfies the equation del f del t is equal to curl of v cross f, the flux of that vector f is actually conserved in time, implying that any a magnetic field which satisfies this equation, the magnetic flux is an invariant in time, which means that magnetic flux over a certain surface, which is attached to a fluid flow or plasma flow, doesn't change in time. What this implies is that magnetic fields are frozen in the plasma. It implies that plasma flows can advect or carry magnetic fields. It can stretch and twist magnetic fields, allowing the energy in the plasma to be channeled into magnetic fields. This is also one of the reasons why you see these beautiful loops in the sun's corona, where if by some means they light up, and you will soon hear why they can light up, the lit up plasma, essentially by virtue of the fact that it is attached to magnetic fields, allows you to image magnetic fields directly in the sun's outer atmosphere. Let's talk a little bit about Mhd equilibria, because this is important for the outer solar atmosphere. So we have the Navier-Stokes equation, and now if you're talking of a system which is in equilibrium, the forces are balanced out, then you would expect that there would be no flows, there'd be no evolution in the system. So all the del del t terms would also be zero, and the flow terms would be equal to zero. So if you put those terms, the del del t terms and the flow terms to be equal to zero and neglect gravity, then this Navier-Stokes equation reduces to this equation, which is essentially expressing the fact that the gradient in the gas pressure is balancing out the magnetic forces in the system. Okay. Now, in this context, the plasma beta parameter is very important. The plasma beta parameter is the ratio of the gas pressure to the magnetic pressure. So when the plasma beta parameter is high, this implies the gas pressure dominates the dynamics, the balance of forces. Whereas if the plasma beta parameter is very low, this implies the magnetic fields dominate the dynamics. Okay. So in the interior of the sun, because of the high density, the pressure goes, is linearly proportional to density. You're dealing with a high beta plasma because the gas pressure is very, very high. So essentially, it's the gas flows or plasma flows in the interior of stars, which determine the dynamics of magnetic fields. They dominate over the dynamics of magnetic fields. So these two conditions, the magnetic Reynolds number being very large, as well as the plasma beta parameter being very large, allows the plasma flows to govern the dynamics of magnetic fields and allows the extraction of the energy in the plasma flows into generation of magnetic fields through the magnetohydrodynamic dynamo mechanism. This is important. Of course, one can then model this magnetic field generation in the interior of stars, and you see the result of such modeling utilizing this Mhd equations in the sun's interior, which is showing here the generation of the toroidal component, and the toroidal component of the magnetic fields is the toroidal component which emerges buoyantly to form sunspots, which is at the at the basis of much of solar activity such as solar flares and coronal mass ejections. We can also push these models to make them data driven. So we drive them with data. Once you drive these theoretical models with data, they become predictive models, and you can make solar cycle predictions. So for example, here you see such a prediction from a combination of different magnetic field evolution models in the sun's surface and its interior, which shows that we are able to reproduce the past solar activity. We are also able to forecast the future solar activity. We will soon know whether we are right or wrong. So our forecast for solar cycle 25 is that it's going to be just slightly stronger than the previous solar cycle. Okay, if you go to the solar atmosphere now, beyond the interior, because of the fall in density, the gas pressure falls dramatically. When that happens, remember this force balance here. So you can basically neglect this left-hand side of the equation, and this becomes 0. And the new equation essentially, becomes curl of B cross B is equal to 0. That's the force balance in the corona, right? The trivial solution, of course, is B is equal to 0, which you shall ignore. But two other solutions are that the curl of B is equal to 0, which implies that there are no currents in the system. So these are known as potential fields, and for a MHD system with magnetic field, the least energy that you could have is in such potential field systems. You also have another solution where your curl of B is proportional to scalar, which is alpha times B. This implies that you have currents in the system and the currents are field aligned. So the currents are in the direction of the magnetic fields. A non-zero finite value of alpha also implies you have sheared non-potential structures which are twisted with excess energy. And if you can tap into that excess energy, then you can release them during a plasma relaxation process when the magnetic fields self-evolve to remove the stresses, to balance out the forces. You can release this energy in the form of thermal energy or energy to accelerate particles, and this ends up contributing to the million-degree solar corona in spite of the surface being 6,000 degrees. So these plasma relaxation processes generate heating through a process known as magnetic reconnection eventually, which heats up the outer atmospheres of stars and also drives solar winds. So how does this occur? So when the magnetic fields in the outer solar surface in the corona are evolving to remove these stresses or through foot point motions, often you can have magnetic fields which are oppositely directed coming together. But remember the divergence of B is equal to 0. You can't really have magnetic fields pointed in multiple different directions. So when you do that, you create an X point where the magnetic field is destroyed and reconnects, and new flux loop systems are formed which retracts away. And the magnetic flux that is lost, the equivalent of the energy that is lost there, is converted to thermal energy, energy that heats the plasma and it radiates, and therefore the corona is bright in X-rays and in extreme ultraviolet and in ultraviolet. When you have a large magnetic reconnection event, you can have enough energy to drive a solar flare or eject an amount of plasma from the corona, driving a coronal mass ejection. And this is how you drive these large-scale eruptions from the sun. Each of those eruptions can in principle have the energy equivalent of like 500 million atomic explosions occurring at the same time. It seems surprising, but if we just look at the amount of energy content in a cylindrical flux loop, which is, let's say, about the size of a sunspot with a radius of 10,000 kilometers and a separation between the two sunspots of about, it's 50,000 kilometers, and look at the volume and take an average field strength of 1,000 Gauss and estimate the energy, you'll realize how much energy content is there. And if you can annihilate that and convert that into other forms, you have this enormous source of energy that can not only heat the corona, but it can also drive solar flares and coronal mass ejections, and also be a source of energy for powering the solar wind. One can develop models. For example, what you see here is a potential field source surface model, which is based on extrapolation of the magnetic field from a solar surface flux transport model. And look at how this compares with observations. Solar eclipses provide us with a good opportunity to compare these observations with the model outputs. And here you see one of our models being compared with the eclipse of 2017, which was the Great American Solar Eclipse. And you see a good correspondence between the magnetic fields and the background intensity that was observed during this particular solar eclipse. When you go beyond the immediate solar corona, the solar wind gets accelerated into supersonic speeds, and the dynamic pressure in the solar wind increases. Eventually, this overcomes the magnetic field pressure, because the magnetic field is also falling off as 1 by r square as you're going out away from the sun. And therefore, it starts dominating over the magnetic fields again. So we switch from the interior of high beta plasma to the exterior in the corona of low beta plasma, and then again to a high beta plasma out in the solar wind. Right? And this is this high beta plasma, the solar wind, which then impacts with planetary magnetospheres, and then creates all this effects of star-planet interactions that also one can, in principle, study using models. Here is a model, for example, which was constructed by various people in SESI and with fundamental contributions from Shujan Das, who is attending this conference, which is a star-planet interaction module, looking at how does a supersonic stellar wind, which is magnetized, shape the magnetosphere of a planet like that of Earth. You see the nice magnetoidal structure, the current sheet in the magnetosphere, in the magnetotail region, and more importantly, you see the squeezed magnetic field lines of the Earth's magnetosphere in the day side facing the sun, where the magnetic field pressure increases because by virtue of the fact it's being squeezed, and then balances out the dynamic pressure and the magnetic field pressure in the solar wind, reaching a dynamic equilibrium in the sun-facing side. This literally stops the stellar wind in its track and protects the Earth's the inner magnetosphere and the atmosphere from the onslaught of the solar wind. This is important because this protects our Earth's atmosphere from erosion due to the solar wind and allows the planet to be habitable. One can look at Mars and what goes on in Mars, because Mars does not have a magnetosphere. And what we find is that if you have a stellar wind impact on a planet which does not have a global magnetosphere, first you form an imposed magnetosphere. But these imposed magnetospheres are different from intrinsic magnetospheres in the sense that the field lines and the plasma attached to these field lines, the imposed magnetosphere, continuously slipping past the atmosphere of the planet. And when it does so, it erodes the planetary magnetospheres, and therefore the atmospheric mass loss rates are somewhat higher. And therefore the planet is prone to atmospheric mass losses over millions to billions of years. And this is what you see in the present Mars, that the Mars currently, which does not have a global magnetosphere, does not in fact also have a global atmosphere. It's a very thin carbon dioxide rich atmosphere, which is only about 100 meters in depth. Okay, so this is my final summary. So I wanted to give you a sense of the physics of the processes that generate magnetic fields in the interior of stars, and also the physics of the processes that occur in the exterior or the coronae of stars, giving rise to coronal heating, giving rise to magnetic reconnection processes which drives solar flares and solar storms, as well as the solar wind. It's important to realize that eventually the space weather that we see at Earth is created through these physical processes deep in the interior of a star, which is far away from us. And studying this genesis of this activity and understanding this in the context of the solar system, where you have enormous data, where you have many observations, provides a window to actually understand such interactions in systems beyond the solar system, in exoplanetary systems, and understanding the habitability of planets and exoplanets under the influence of changing space environment over billions to billions of years, which transcends this time scales between space weather and space climate. And eventually, this has an influence not just on our planetary technologies, but also on the possibility of life in planets. All right, I just wanted to end with that, and thank you very much.
Thank you so much for the talk. There's a question in the chat box from Ankush. Dian, can you hear me?
I do hear you, and I'm trying to read
Okay,
that question.
right.
Suppose there are sudden changes in pressure in seconds time scale. Do you still expect to have magnetic and pressure balance valid? I mean, how much time it will need? Okay, so it really depends on the sound speed, right? So how are pressure imbalances wiped out? The only way you can wipe out pressure imbalances in a fluid is by propagation of the sound, right? So the question that we're asking is a question that is dependent on the time scale. So my answer to your question would be, if you induce a pressure imbalance or a sudden change in magnetic pressure or gas pressure, which is happening at a time scale which is much shorter than the time scale for sound wave propagation through that medium, then you will not be able to attain this equilibrium. On the other hand, if your changes are happening over a time scale which is much slower than let's say L by CS, where CS is the speed of sound, then you're allowing the balance to occur because you're allowing this pressure to be distributed across the system. Right? So it's a question that's dependent on how fast is the process and
Yeah.
time scale of the sound speed.
Yes, that is true. So actually, it will depend upon system length scale also, right? Means it will not be very instantaneous pressure balance. It can take longer time to get into balance.
Right.
So what we think about,
as well as the speed of sound. Typically, this is very large inside the sun, of course.
Sun, right? So like
So you
sometimes
expect
like
that pressure balances will occur pretty quickly.
yeah. So we have means I just wanted to say like we may have like many times not equilibrium conditions
Absolutely. Yeah.
in solar
Typically in magnetic reconnection processes where changes are happening extremely fast,
yeah,
you don't expect to have any sort of equilibrium.
equilibrium.
Yeah.
And that is
Especially
also
when
one.
expands are current sheets, you don't expect any equilibrium.
In equilibrium, right?
Yeah.
So one more about magnetic reconnection. So that was like we model with MHD, right? But the magnetic reconnection is microscopic, more like a very small scale process, which we try to understand with MHD. So how accurately we can model actual magnetic reconnection with MHD?
So well, I mean, you see, MHD has certain approximations, and these approximations will break down the smaller your scale is.
Yes.
So if your current sheet is very thin, right, and very close to a current sheet, you are really, and particularly your electric fields are humongously strong, right? I mean, typically in MHD, we don't deal with electric fields because you expect the electric fields to be pretty low, given that you're in a highly conducting regime. But in a current sheet, you expect strong electric fields to manage it. So often in MHD systems, for example, if I can just show you this simulation again, we are very good at telling you where the current sheets will be, right? Yeah. For example, we can tell you that the current sheet will be here by looking at the distribution of J, the global current density distribution, also the magnetic field configuration. But we will not be able to tell you the dynamics of individual charged particles very close to the current sheet through the MHD. Yeah. For that, what you would need is particle incidence simulations. So you have coupled particle incidence simulations, or you have adaptive mesh refinement where we hold on to this current sheet and you take the boundary conditions from the large scale Mhd model and put them into a PIC model, and then look at the motion of charged particles around the current. So there are ways to go around them technically through modeling, but yeah, the Mhd approximations tend to break down very close to a current.
Close to it. Yeah, that is their limitation they have, right? Yeah, thanks.
You're welcome. I see there is another question from Ashwin Amrita Raj. Does the magnetic field relaxation and nanoflares solve coronal heating problem, or is it still remains a mystery? Okay, so my view of the coronal heating problem is that it's a problem, but the problem is not the problem that it was about 10 years back. About 10 to 15 years back, the problem was, it was an enigma of what hits the corona, because the surface is 6,000 degrees and the corona is 1,000,000 degrees. And a lot of people still in that inertia think along the same lines and say that, oh, you know, the surface is 6,000 degrees, the corona is 1,000,000 degrees, this is a big problem. Well, if you're thinking thermodynamically, classically, forgetting about magnetic reconnection and waves is a big problem. But for solar physicists, I don't think it's a big problem. It's a problem of overabundance. Now we know that both magnetic reconnection, flux due to the Poynting flux that's there in the magnetic fields, also for AC heating, waves carry enough energy to be able to sustain a 1,000,000 degree corona. I think the problem now has really become what is contributing what fraction to coronal heating. I think that is the open question, and I think the consensus right now is that magnetic reconnection certainly is playing a very important role, because it's a process that occurs everywhere, is ubiquitous in the corona, and you see it happening from finer and finer scales. The more higher resolution instruments we have, we seem to notice finer and finer nanoscale reconnection events. For wave heating model, of course, this is certainly possible. We see waves also in high spectral resolution, high temporal resolution instruments. The problem there is to figure out how to damp the waves. I mean, waves carry energy, but let's say you have waves passing through the room, right? Unless you are able to damp and kill the waves inside the room, your room is not going to get heated. The waves will carry the energy out of the room, right? The same stuff works for the corona. Unless you're able to stop the waves, kill them, and extract their energy out by damping them in the corona, you're not going to be able to hit the corona. So the open questions there are what damps the waves, what can essentially stop the waves and extract the energy in the waves and hit the corona, instead of allowing them to leak out into the outer regions. So that's the more important questions that confront us. I think about the energy budget, there is no problem. I mean, there's more energy than we need to hit the corona. The question is, what is contributing what? That's the problem. Yeah, I see some raised hands, so you can, I think whoever, if you have a question, just go ahead and ask. I see Ankur.
Yeah.
Yeah.
Yeah. So one more like about the solar wind. So where we stand now, like whatever we understand solar wind origin or Parker's equation based on that. So current understanding, do we understand how it originate, how we accelerate? What understanding we have now?
Yeah, I mean, let me get back to this particular slide here. Okay. So if you think of the science of the solar wind, I mean, what does it take to drive a flow? What it takes to drive a flow is pressure differences, right? A pressure gradient, right? I mean, if I can produce a pressure gradient, it works in a tube. It works in a tube. It works here. I can blow. I'm creating a force, a pressure difference. I blow the wind. It works even for stars, right? Okay. Now, what are the sources of the pressure difference, the pressure gradient that you create, are the and how and how anisotropic is this pressure gradient that you're creating on the near surface layers is the challenging part to understand, right? So eventually, you know that if you solve the Parker's solar wind equations, that if you have a pressure gradient, you will eventually have a supersonic solar wind. The question is, what is the structure of that wind? What is the amplitude of that wind? And how is that governed? The amplitude of the wind implies that you're talking of energy, right? Because the speed of the wind is and the flux, the matter flux, half rho v square, is really related to how much energy is being fed into the wind, right? So that depends on where is the energy being created. So energy can be created by acceleration of magnetic fields. It can be created by nanoflare heating. It can be created by waves generating heat by being dissipated. It can also be created by mass loading from the chromosphere. So chromospheric specules, which are jets, essentially accelerates matter into the outer layers at speeds which can exceed the escape velocity and feed the solar. So again, the challenge there is to understand how does the photospheric non-uniformity of magnetic fields, the non-uniformity of closed and open structures, as Vishal was talking about in the solar corona, and the relative contributions of mass loading from the chromosphere, localized heating in the corona, how much of that contributes to the structure? By structure means spatial distribution and amplitude of the solar wind. I think that's a problem that is far from being resolved. This is something that we still are working on to look at the fine scale structure. Global variations, large scale spatiotemporal average predictions of winds, we can do fairly well. But to look at the fine scale structure and acceleration processes near sun is something that's still an open question. And Parker's solar probe has thrown up certain more interesting observations, which makes us believe that it's possible to also accelerate solar wind in situ or out away from the sun through various processes, which is another new information or enigma that we're trying to figure out. So I think the solar wind acceleration process is something that will take a few, maybe this decade is the decade of solar winds. We will try to figure this out. I think we'll make important progress in our understanding.
Yeah, that's true. Nice.
Thank you, Rian. And I don't think there are any more questions.
Okay.
So we'll probably stop this session for now, and we'll meet. I hope to see you all after lunch in the ML lecture series.
Shall we, Yoshita, make it 2:15?
Yes.
Because I think it will take us some time to have lunch and then come back. So shall we make it 2:15?
Yeah. Okay. So see you all at 2:15. For the ML lecture series 2. Okay.